All right, here we're going to look at section 1.2 is where we're going to start out on this. And basically this is working with functions. It's more, kind of prereq stuff that we should know, all this stuff. We just want to make sure that, um, you know, that we've got this. Um, anyway, so if I have, uh, first of all, let me go back to number 47 in section 1.1. That was the function u of x equals 1 if, oh, come on. U of x equals a split function. It's 0 if x is less than 0, and 1 if x is greater than or equal to 0. Greater than or equal to 0. All right. And so basically what that looks like is this. So it's a horizontal line, right? It's the x-axis going left of the origin, and it's a height of 1 going to the right of the origin. All right. So anyway, the kind of going in, it asks what u of x minus 1 is. Well, that'd be a left shift because when you plug in 0, you'd actually be getting -1, which on the graph is 0. So this is actually a left shift. So it looks like this, excuse me, a right shift. If you plug in 1, we get 0. Sorry. So kind of that pivot point starts out here. So this is a right shift, and then going left there, and then this is u of x, and then kind of the one that maybe part D was, hey, what's u of x minus u of x minus 1? And kind of the easy way to do this is with pictures, not with like plotting points and stuff like that. But basically you can break it up into sections. So if I'm left of the origin, what's u of x? U of x has an output or a height of 0, right? And if I'm left of the origin for u of x minus 1, I also have a height of 0. So certainly 0 minus 0 is going to maintain and still be 0 here. And then what we got to do is figure out what happens at the origin. At the origin, this one has a height of 1 because I actually hit that height. The u of x minus 1 has a height of 0. So at the origin, I have a height of 1. And then that's going to be the case where u of x, until I hit x equals 1, is going to be 1 minus 0, right? So I'm going to stay at a height of 1 until I get over to 1. So we do need to figure out what happens at 1. If I plug in 1 on u of x, I get 1. If I plug in 1 on u of x minus 1, I also get 1. So 1 minus 1 is 0. So that'd be an open dot, and it drops back down. So this needed to be an open dot on the actual origin there because the height there is 1. And then it's everything to the right. But that's kind of how I do it, how I think about it. And anyway, so we have that kind of horizontal line up at a height of 1 between 0 and 1, and it's got it includes 0, 1 on the graph, but 1 1 is not included on the graph. That's an open dot. Anyway, if you're looking at, what's the domain of u? The domain of u would be all real numbers, right? Or I know some of you really like that interval notation. You can write minus infinity to plus infinity. But what's the range of u? The actual outputs. So if we're just looking at this one, the actual heights that you hit are just 2 points, 0 and 1. So if we have a set of elements, we use set notation. So the set including 0 and 1. Those are the only 2 heights that we hit. Okay, so hopefully that makes sense. So that was kind of finish up on number 47 in the first section. So now let's go on to new stuff. I'm gonna try and fly through this if I remember how to use. Let's see. There's a clear screen somewhere. There we go. And hopefully it lets me draw again. All right. So in section 1.2, we're looking at different things like sum of functions, difference of functions, product, and quotient of functions. And then those are pretty basic definitions, but then we got composition of functions, which we've all done. But let's let f of x equal x squared minus 3 and let g of x equal 2 minus x cubed. Okay, so let's do something, actually let's do x squared plus 3. So I'll do something a little bit different than what I've got in the notes. But anyway, so we have definitions. So definitions, this is the way it has to be because we define it to be that way. But the sum of functions, what does sum mean? Sum means add, doesn't it? So the sum of functions, we're going to add these functions together. So instead of adding numbers, we're actually adding f of x and g of x together. So this is defined by f plus g evaluated at x is going to be the sum of functions, and by the definition, that just is equivalent to f of x plus g of x everywhere that is okay on the domain. So this is what it's going to be. Pretty basic stuff. So in our case up here on the example, f of x plus g of x is going to be, so in our case, f plus g evaluated at x is going to be x squared plus 3 and then plus 2 minus x cubed. Now you could put parentheses in here. I'm adding this whole thing, but we don't really need them, right? So when you add something, you can just drop the parentheses. But I'm going to not leave it like that because I've got a plus 5 there. So I might rewrite this as minus x cubed plus x squared plus 5. Would be kind of a simpler way to write that. So in descending order, I'm going to write down my functions just so I can keep using these three as I'm giving examples. And then we have the difference of functions. So maybe I'll just stay on this page and use, if I have the difference of functions, I'm going to subtract them. So the difference of functions, basically f minus g evaluated at x is going to be f of x minus g of x. So what would f minus g evaluated at x be for this function? Well, f of x minus g of x, here's f of x, is x squared plus 3. And then I'm going to subtract the entire quantity of g of x. So notice f of x minus g of x is the whole quantity. So I'm going to subtract this entire quantity. So here I have to have parentheses because I'm going to subtract it all. Okay, and then of course, what can we do with subtraction? We can add the opposite and change those signs in there. And then if I wanted to kind of change this up, what would that be? It would be a positive x cubed. So this is going to equal a positive x cubed plus x squared, and then plus 3 minus 2 is going to be a plus 1. So that would end up being x cubed plus x squared plus 1. By the way, the domain of f is all real numbers. The domain of g is all real numbers. The domain of f plus g is all real numbers, and down here, and the domain of f minus g, that kind of look like a multiplication sign, but is also all real numbers. All right, so pretty basic stuff, right? This is, you're like, wow, I'm glad I'm doing calculus because this is so easy. All right, anyway, but this is just algebraic review and definitions. Okay, so now let's go and say, okay, what about the product of functions? Okay, so let's define the product of functions. Product means multiply, right? So the product of f and g, product of two functions, f times g evaluated at x, so that is a raised dot, is going to be f of x times g of x by definition. So in our case, what would it be? It would actually equal x squared plus 3 times 2 minus x cubed. Okay. Once again, the domain of all of f is all reals and g is all reals, but the domain of f composed or f times g of x, the product of f and g, is also all real numbers. There's no x's that are going to be excluded. We're going to be able to keep those in there. And anyway, if you wanted to, you know, the book's going to probably multiply this out. This is good enough for me, unless we need to simplify or keep going. But anyway, if you FOILed that out, what would that be? That'd be equivalent to you take x squared times each part, so 2x squared minus x to the fifth, and then plus 3 times all that, so plus 6 minus 3x cubed. I believe that would be, and then you could write it in descending order if you want. So minus x to the fifth minus 3x cubed plus 2x squared plus 6. So anyway, this is good enough for me. I mean, they're the same thing, but if you're working an odd exercise with an answer in the back, you're going to want to make sure that your answer is equivalent to their answer and go from there. What about the, instead of product, what if we have the quotient of two functions f and g. So f divided by g evaluated at x is going to be f of x divided by g of x, where what do we know? We need one more thing. The denominator can't be 0, right? So g of x cannot equal 0, because it'd either be 0 over 0, which is indeterminate, or it would be something else over 0, which is undefined. So what would that be? Well, this would just be x squared plus 3 over 2 minus x cubed. So let me just rewrite that here. F divided by g evaluated x squared plus 3 divided by 2 minus x cubed. And then, you know, that doesn't really factor out very good. So if you could factor top and bottom, sometimes you can get some things to cancel out. But if I'm looking at the domain of this quotient function, we could write that as the domain of f over g. What do we know? We know that it's, here's one way. This is called set builder notation, but I could say we could plug in the set of all x's such that. So sometimes they use a colon, but usually you're going to see a bar there. The set of all x's such that what? 2 minus x cubed is not equal to 0. Now we could probably do that a little bit better. So any x is going to work as long as 2 minus x cubed doesn't equal 0. Well, when does that happen? Let me just clear this off. Come back. If I have 2 minus x cubed, if it does equal 0, then that implies if I add x cubed to both sides, x cubed equals 2. If I take the cubed root of both sides, x equals, now I got a question for you. Is this plus or minus or not? But x is going to be the cubed root of 2. Could I put plus or minus there, or do I or not? Like I do when I take the square root, do I do that for odd powers?
You don't need to.
No. Actually, minus wouldn't work, because if I have minus the cubed root of 2 and I cube it, it's going to be minus the cubed root of 2, and then minus that is a plus. So it'd be 2 plus a positive 2, which is positive 4. But remember, the cubed root graph looks like that, right? It's a swerve flipped around the y equals x axis, and so we're over here at the cubed root of 2 for x. There's only one of them, there's only one output for that. So anyway, we could also say the domain of f over g is the set of all reals excluding, so sometimes when you only eliminate a few of them, I like to just list out the ones that we exclude. So we can say the set of all reals excluding the cubed root of 2, or that would be equivalent for you interval lovers, minus infinity to the cubed root of 2, but I can't include it, union or along with the cubed root of 2 all the way to infinity. Okay, so that's another interval way. Both of these, along with kind of the set builder notation that I gave you on the other page, are good ways to show what the domain is. Personally, I don't care which way you do it. I just want you to follow me when I'm doing it different ways. But I'm okay with any of the notations that I used for domain and range, because it is going to ask you that a lot. Okay. And then, you know, what, I guess I'm going to look at an example, another quick example. I've got another one with quotient in there that's pretty good, but what if I have this? What if I have, for example, let's say I have f of x equals, and I won't write f of x every time, but if I've got, oh, never mind. I don't want to do this yet. I'm gonna do this for composition of functions. So forgive me on that. Anyway, this is pretty basic stuff so far, right? So kind of duh material, but now we're gonna get into you know, stuff that's a little more involved. So let's look at composition of functions. So we're going to define that, composition of functions. Once again, you've been using this for a long time, but you don't really think of stuff as composition of functions. And there's some calculus results and theorems. I'm going to abbreviate functions. Composition of functions. What is that? This is going to be f composed with g. Once again, and you know I've got the student notes in there too, so I'm not necessarily going to write everything down. I do expect that you reference those. But this is f composed, so that's a raised circle there. Hopefully you can see that plus sign moving around. Anyway, this is going to be defined to be f evaluated at g of x. So we can really say both sides of this the same. F composed with g of x is f evaluated at g of x. So another way you could, the shorthand way to say that is f of g of x is f of g of x. So that's kind of a shorthand way to say that, but it's really f evaluated at g of x. Just like if I have f of 2, it's f evaluated at 2, right? We plug a 2 in for an x. Anyway, so let's go and say, all right, what is, let's just figure out what f composed with g evaluated at x is for our example. Well, our example was, what is g of x? And I'm going to use some color coordination here, but g is green. So this is, g was 2 minus x cubed, right, in my example that I was using. So it's going to be f evaluated at 2 minus x cubed. Well, what's f of x? F of x was, if you remember, x squared plus 3. Well, f of anything is that anything quantity squared plus 3. So if I'm saying f evaluated at, this is my anything, 2 minus x cubed, what's this going to equal? This is going to equal 2 minus x cubed quantity squared and then plus 3. So once again, this is what I'm plugging in for x. Everywhere there's an x, I'm going to plug in 2 minus x cubed. Okay, so hopefully that makes sense. Now we could leave it like this. This is just fine. In this case, I would probably leave it like this instead of squaring it out. If you wanted to square it out, the FOIL becomes the full, and it'd be 4, and then the outer and inner you multiply together and double, so minus 4x cubed, and then plus x to the 6th, and then plus 3 at the end. And then, of course, I could put this as 4 plus 3 is plus 7, right? So I could have something like that. That's no better, so I probably wouldn't do that. But what we do need to do is note the domain of f composed with g. So in this case, we don't really have any issues or problems because this is f composed with g is right here. The domain of f's all reals, domain of g's all reals. Is there any problems here? So I always try to eliminate the problems, right? There's no problems for plugging in for x, but you do have to look at how you get there. So we got to be careful if you're coming all the way and simplifying to this bottom version. You know, it might look really nice, but in this case it is nice, so the domain is actually all real numbers. But I'm going to give you an example where it doesn't work out so well on that. So let's look at one more example. If I have f of x equals square root of x and g of x equals x squared. What do we have here? What's f composed? F composed with g evaluated at x. Well, this is going to be f evaluated at g of x, right? So once again, the g of x plug in here. So this is f evaluated at, and I'll use green for g, f evaluated at x squared. Well, everywhere there's an x, I'm going to plug in what? X squared now. Okay, so this becomes f fuchsia. This is going to be the square root of x squared. Well, what is the square root of x squared? Well, it's the absolute value of x actually. So we got to be a little bit careful there, because you can't just say it's x, because if x is positive, 5 squared is 25, square root of 25 is 5. But what if x is negative 5? Negative 5 quantity squared is 25. And what is the square root of positive 25? If you have the square root symbol already there, it's the principal or positive one, and that's 5. So we got to be a little bit careful there. So it's actually the square root of x squared by definition is the absolute value of x. Now you might say, well, what's the domain of f composed with g? Well, for this, it's all real numbers, right? But what about for this? That you got to look at how you got there. Well, if I plug in any x and square it, I'm going to get a positive number, or 0 would be the smallest. I'm okay to take that square root. So it is all real numbers here. So what I actually want to do here is I want to flip the script, and I want to look at what is g composed with f, and does that change anything? So let's look at that. So let's look at, if I do g composed with f evaluated at x, by definition, this is going to be g evaluated at f of x. So if I'm remembering my functions right, this is going to be g evaluated at the square root of x. Okay, because that's what f was. So I've got my square root of x, and then of course g of x was x squared, right? If I'm remembering it right. So g of anything is that anything squared. So this is going to end up being the square root of x quantity squared, right? And what's that equal? That equals x, right? So g composed with f evaluated at x equals x. Now you might say, well, hey, the domain's all real numbers for g composed with f. But the reality is it's not. So the domain of g composed with f does not equal all real numbers. So we have to be careful. Why is that? Because you got to look at how you got there. So how I got there is right here. Okay, so what values of x's can I plug in? Well, I'm going to take the square root of x. So the domain of g composed with f, because I have to take the square root of x before I square it out, is the set of all x's greater than or equal to 0. So including 0 to infinity, if you like interval notation, or I could say the positive real numbers including 0 is kind of my shorthand way to do that. Okay. Another way to do that, like the book would probably say, positive reals union the set containing 0, which that's just a lot of writing when I could do a shorthand like this and say that's okay for you. All right, does that make sense? Any questions on that? All right, so take that as a no. So just trying to be precise on domain and range. So let me go back, and I got to look at my note. I meant to print off my notes. I'm actually not at DMAC, I'm at my other office, but anyway, so what is, let's just note something about the domain. And let's just talk about f composed with g. The domain of f composed with g is the set of all x's. So the domain's always a set. The set of all x's that are in the domain of g, because what do I do first? Let's just write that down. F composed with g evaluated at x is f evaluated at g of x. What do I do first? What I do first is I do what's in the parentheses first. I do the g first. So my x's that I can plug in have to be able to be plugged into G. So basically, we have to say it's a set of all x's that are in the domain of G. And then after we put them into G, we get outputs, which is the range of G. Where do I put the range of G? I put it into F, right? So we also have to say that that the output, so such that the G of X would be allowed to be an input into F of X. So G of X is an element of the domain of F. So we got to be able to plug that in. So what's that really saying? What that really saying is, thus we can say that the range of G, which is the set of all outputs when you plug it into G of X, has to be included in the domain of F. So that has to be a subset or included of in the domain of F. So every output of G that we get, it needs to be able to be plugged in to F. So I'm going to draw a picture of that, hopefully. So this is working out pretty good so far. But if we have, let's look at kind of a mapping. So the first thing we do is if we have our X right here, here's our X. What if we have F composed with G? So this is F composed with G. What am I doing first? What function do I do first? G, right? Because it's F composed with G of X is F evaluated at G of X. So I'm doing the G of X first. Okay. And then, so I end up at an output G of X, and then what do I got to do there? Then I got to be able to map that by F into the output, which is F composed with G evaluated at X. But the reality is, could I have, if F is fuchsia here, so could I have more things that I could plug in? Sure. But basically all the outputs from G, which is the range of G, might be right here in that green. I could take more than that possibly, which this red would be like the domain of, excuse me, that's supposed to be red. The red circle is the domain of F, but my outputs from G, the range of G, has to be included in there. Okay, and then what is my final deal? Basically, what a composition of functions does is it takes the initial and it gets to the end. But notice the G was first, then the F, but this is the function F composed with G. So basically, we're trying to eliminate the middleman and go from the beginning to the end along the way. Okay. All right. And then we could plug in specific numbers as well. So let's just do, let's just stick with that one I was talking about when we had F was square root of X and G was X squared. Okay, we could have what was F composed with G of X was the absolute value of X, right? So if I said, hey, what's F composed with G evaluated at 2? Sorry, it was the absolute value of X. Well, this is going to be the absolute value of 2, which is 2. So we did the work to figure this out. What's F composed with G at negative 2? It's the absolute value of negative 2, which is 2. Okay, so what if we stepped it along the way? Because when we stepped it out to figure that out, it was F evaluated at G of X, which was F evaluated at X squared, right? So what we could do first is on this, if you wanted, let me change colors here. If we wanted, we could say, hey, for this, by definition, this is f evaluated at g of 2. Well, what's g of 2? We plug a 2 in here, right? So this is f evaluated at 2 squared, or f evaluated at 4. Well, what's f evaluated at 4? F of 4 is the square root of 4, and since the square root symbol is there, it's a positive 1, that equals 2, and that's what I had. So we could take any of these and step them out. Let me do that here as well. Let's just do it with this one. F of this, by definition, is f evaluated at g of negative 2. Oh, what happened there? My screen's getting big on me. Anyway, what's g of negative 2? I can widen, or did the screen move for your eyes? Because it did for me. I was like making it bigger and smaller. Anyway, g of negative 2 is negative 2 quantity squared. So this is f of, come on, f of negative 2 quantity squared, which is also f of 4. And what's f of 4? Square root of 4, which is 2. So we also got that down there. Okay. All right. So sometimes things can be a little awkward, but anyway, let's flip this the other way. I think I have an eraser function. I'm just going to see if I can erase. Keep these on here. Yeah, that's not, I don't like it. Let's just clear it off. And then let's just one more on this. And let's just look. So what do we have? We had f of x was x squared, wasn't it? Or was that the square root? That was square root. And g of x is x squared. So let's look at g composed with f at 2 and g composed with f at negative 2. Well, if you remember, g composed with f evaluated at x was x, right? So you might say, hey, this is 2 and this is negative 2. But that's going to end up being a problem. So let's look at why that ends up being a problem. Let's look at this one. This is g evaluated at f of 2. Well, what's f of 2? F of 2 is the square root of 2. So it's g evaluated at the square root of 2. And then now I'm going to plug that in. Come on. I'm going to plug that in here. So this is the square root of 2 quantity squared, which is 2, right? So that was fine. This one ended up being okay. But the problem is going to be this other one. So let's, I'll use black, I guess. Anyway, what about this one? This is g evaluated at f of minus 2, which is g evaluated at the square root of minus 2. Well, the square root of minus 2 does not exist, right? So we can't get an output of that. So what did we say? The domain, remember we said the domain of g composed with f was including 0 to infinity. So when we get things, you got to be a little bit careful, because if I'm plugging in something that's not in the domain, it's probably not going to work out well for us. So that's why I wanted to show that. All good? All right. Time for a quick little, let's see. I was going to ask you some questions, but we'll do that at the end. I get through some stuff here. So need to get through just kind of real quick reminders on any algebra stuff. Let's see. What are linear equations? Hopefully you read this stuff and you should all know it. I'm going to make you chime in. Somebody give me a general equation for a line.
X.
Y equals X, that's a specific one. Can you give me one in general? Y equals X is a specific line with a slope of 1 and a y-intercept of 0. Anybody else?
MX.
What's the slope? Say it again.
MX plus B.
Y equals mx plus b. You bet. So y equals mx plus b, this is old slope-intercept form, right? M is the slope, it's rise over run, it's delta y over delta x, right? And then b is my y-intercept. Because if I plug in 0 for x, I get y equals b. So the y-intercept is 0b, is always on your graph, right? And then if the slope is positive, it goes uphill left to right. If it's negatives, it goes downhill left to right. If the slope is 0, what do you got? You got a flat line, right? Right, like your pulse right now. Beep. Anyway, what if I got a vertical line? Slope is undefined. So the run would be 0, so it's undefined. So you'd take some fixed number, positive number, probably, depending on which way you're subtracting, positive or negative, fixed number divided by 0 is undefined. So a vertical line has undefined slope. Some books say it has no slope. That's kind of bad because sometimes we think of 0, like I have 0 money, I have no money. So that's just bad English. Okay. So this has a slope of 0, horizontal line, vertical line has undefined slope technically. All right, so we got all that. What are some other equations of a line? We also have y minus y1 equals the slope times x minus x1. So if x1 and y1 are any particular point on the line, and m is the slope, we could use this equation. So if I have slope equals 3/4 and 2, -3 is on my graph, then I could come up with the line as y minus y1. So y minus a -3 is y plus 3 equals the slope, which is 3/4 times x minus x1, which is 2. You do not have to take it over to the y equals mx plus b. If I'm just asking for an equation of a line and you have a point in the slope, use this and be done. If you're doing an odd exercise though, they're gonna always change it over to the good old-fashioned standard slope-intercept form. So this is called point-slope form because if you have a point in the slope, you can come up with a line. This is slope-intercept, which we used all your high school years, right? And then we've also got standard form, and that would just be the pretty form. So like a lot of people don't like fractions, so we can clear it out by multiplying through by 4 and then get all your x's and y's on the left and all the numbers on the right. So ax plus by equals c, where a, b, and c are constants. That's standard form, which is the pretty form. Okay, so we could always do that if we need to. All right, and then what are some other things that we have? We have polynomial functions. So let's just kind of talk about those quick. What's a polynomial? Those are really nice when we graph them. So there's no sharp points or things like that. Domain is all real numbers, but it's going to look like this. F of x equals a sub n, which is just a constant, x to the nth power, plus a sub n minus 1, which is just some other constant, x to the n minus 1 power, and we keep going all the way down to a sub 2, x squared, plus a1x to the first, plus a sub 0, which is just a constant. So examples of this would be like 3x to the 4th minus x cubed plus 2x minus 6. Okay, well, what is, so a sub 0 is minus 6 here. A1 is 2. What's A2? Anyone? Bueller? Come on. You guys still there? You awake? Do we need a cheer? Not one person knows what A2 is? Well, what is this? This would be plus 0x squared, right? So A2 is 0. All right, so just because you don't have the term doesn't mean, that it wouldn't be there if you attach a coefficient of 0. All right, anyway, so we got all that. So graphs of these are usually pretty nice. If I have, if the biggest power is even, what do we know? It's going to explode up as x gets huge. Either way, it'll explode up, go out and up forever. Sorry, it's not straight up. It goes out and up forever. If I have an odd one, like, you know, x to the 99th is the biggest power, it's going to go out and up in quadrant 1, but for negative numbers, it's going to go down forever. And then the only thing is how often does it cross the x-axis, but it's going to go nice up and down. So these are polynomials. The domain of polynomials is all real numbers. So we can plug anything into these and get nice functions. They're no sharp points and no holes, tears, rips, etc. So they're nice functions. We're going to use them a lot. So when you have like y equals x squared, that's a polynomial function. Okay, y equals x cubed. So we had some base graph stuff. All right, clearing this out. And then we have rational functions. What's a rational functions? Basically, those are quotients. I'm gonna save it for class, but I'll go through the different numbers. Rational numbers are fractions. Rational functions are the, you know, I'm gonna have, f of x. If it's, well, let's call it rational. So q of x, they like to call it q because q for quotient. But anyway, numerator function divided by a denominator function where n and d are polys. They're polynomials. So basically, what's the domain of a rational function? It's the set of all x's where the denominator, such that the denominator doesn't equal 0. So d of x is not equal to 0, however you want to do that. Okay, so pretty basic stuff there. And then what else do we got? So hopefully this boring as we're ever going to be the whole term, because it's just nothing but a bunch of review. Let's just look at an example quick of that. If I have f of x equals x squared plus 2x all over x. Okay, the question is, what does this look like? Well, I could factor an x out, right? So we want to factor it down. And then what could I do with those x's? I could cancel them, right? So if I cancel these, they cancel out to ones as long as it's not 0 divided by 0. And I'm going to be left with something that is equivalent to x plus 2, but where? On the domain of f, right? So what is the domain of f? Domain of f in this case is all reals except where the denominator equals 0, which is at 0. So we could write it like this. You could write it minus infinity to 0, union, not including 0 to infinity. So union or along with. The other way you could write this is the negative reals union the positive reals, because those don't include 0. All right. Anyway, so don't forget how you get there. And of course, we could have the graph on that. This is just y equals x plus 2, which is this, except we got to be a little bit careful. Now I do need that eraser function. Right there, I need to have a hole, right? So I need to have a hole at 0, 2. 0, 2 is a hole. All right, good to go. And what else do you need to know? Quadratic functions are a type of polynomial functions, right? So if I have f of x equals x squared, ax squared, sorry, plus bx plus c, and I know what you're saying. Why don't they call it a2x squared plus a1x plus a0? Well, we could, but this is just easier because then we end up with the quadratic formula. So if I want to know where that equals 0, if I have ax squared plus bx plus c equals 0, does anybody know where that happens? So ax squared plus bx plus c equals 0 when x equals, anybody? Negative b plus or minus square root of b squared minus 4ac all over 2a. Does anybody know why this is true? Calculus proves it. I'll tell you that. We'll talk about that later. And then the discriminant under here, b squared minus 4ac. If that's greater than 0, we have two roots or zeros or two places where we cross the x-intercept. So if that's greater than 0, we have 2 roots. If it's equal to 0, you have exactly 1 root. And if you have, if that's negative, sorry. So if that equals 0, there's exactly 1 root or x-intercept. And if it is less than 0, then what? Well, square root of a negative number, there are no roots, no real roots. So you do not cross the x-axis. All right. Moving along, starting to run out of time here. I've got a little stuff on sine and things like that, but then we've got even and odd functions, and then I think I'm done. So I'm just going to finish that up quick. And like I said, I am recording this. Hope you all have a great extended Labor Day weekend, but please get through section 1, 2 before next week, because we get into calculus stuff. And so 1, 3, 4, 5, and 6 are going to be not review for most of you. Okay. And so anyway, we just talked about even functions. What's f of x is even. F is an even function if and only if f of minus x always equals f of x. All right, so if I have an example, if I've got f of x equals x squared, basically the best way to check this out, plug in a minus x. Well, I'm going to plug it in everywhere there's an x. So this is minus x quantity squared, which is equivalent to x squared, which equals f of x. So that's always true. So this is an even function. Even functions are going to be symmetric with respect to the, to the y-axis. All right, so starting to lose drawing capability here. All right, there we go. Symmetric with respect to the y-axis. And then we also have f of x is odd, just to finish this up. It's odd if f of minus x equals the opposite of f of x. So if I have, of course, this is not equal to the opposite of f of x, so this is not odd, the one I gave you. But what is an example of something that's odd? Like x cubed, y equals x cubed. So if f of x equals x cubed, what's f of minus x? Well, it's minus x quantity cubed, which is minus x cubed, which is the opposite of f of x. So this would be an odd function. What do we know about odd functions? Odd functions, the graph of that is going to be symmetric with respect to the origin. So if I did a 180-degree rotation about the origin, I'm going to end up on the same graph, same look. Symmetric with respect to the y-axis, if I did a 180-degree rotation here, I end up with the same graph around the y-axis. Okay, what if neither one of these is the case? Then it's neither even nor odd. So just last examples, if I've got f of x equals x squared plus 2, that is plus 2x plus 2x. That is going to be neither even nor odd, because it's not going to be equal to f of x if you plug in, f of minus x is not going to equal f of x, and it's not going to equal the opposite of f of x. So then we call this one neither even nor odd. Okay, so that should be all you need. If you need anything else, WhatsApp me. Have a great weekend. Have some fun, but get the algebra stuff done so we can move on to calculus next week. Ready, break?